Hello, this is Dr. Eidelberg, and today's presentation will be cantilever beam analysis as part of our introduction to finite element analysis. We'll cover in this lecture a problem definition. We'll take a look at an analytical solution for the problem. We see how Inventor Solution gets the results. We'll look at the solution by LISA, Finite Element Analysis Tool. We'll make some conclusions based on the results and also recommendations for our continuation in MET 300. This is an example of a door which is rising up and down with a counterbalance to balance the weight of the door with a pulley and a lever arm which connects the door with the cable of the counterbalance. So we like to do the analysis as part of a design of the lever arm in yellow, knowing that the door weight is 100 kilograms. In other words, the counterbalance at this point will be 1,000 Newton upwards. And then the beam size is 1,000 millimeters, 100 millimeter high, and 20 millimeter wide. The material is aluminum in this case. So to get the analytical solution, we first need to formulate the problem. Now, since this is a simple case, we could easily find the formulation of the missing variables or the variables that are related to the solution process, either from manuals, handbooks, textbooks, or simply Googling. And what we see is that the maximum deflection equals to the force applied at the end of a beam times the length of a beam cube divided by the quantity 3 times the modulus of elasticity and the area moment of inertia. Now, the maximum stress at the beam equals to the moment times the distance from the neutral axis to the extreme point of the height of the beam, which is h divided by 2, half the height, divided by the moment of inertia of the cross-sectional area of the beam. Now, in our case, the upward force is 1,000 Newton, the moment is 1,000 Newton meter, the width is 20 millimeter, the height is 100 millimeters, the length is 1 meter. E for aluminum in this case is 70 gigapascal, and I is given with the quantity B times h cubed divided by 12. Having the formulation, we could go to Excel, submit the values of the problem, and then go to the formulation and calculate the deflection as 2.86 millimeters, and then the stress is 30 megapascal. Now, let's take a look at the results which we showed in previous episode and done by Inventor. We see that the maximum deflection is 2.92. This is compared to 2.86, the exact solution, which is 6% error. Then if we take a look at the stress over here is von Mises stress, and it's given to us here as 29.84 megapascal. The principal stress, which is similar to what we calculate with the analytical solution, is 38.1 megapascal. Now, if we go through the Lisa solution and use 1100 nodes, and as we recall, when we did the analysis on the previous episode, we mentioned that 1300 nodes are free with Lisa. In other words, you don't have to purchase the analysis tools if you use up to 1300 nodes. And then with this number of nodes, we see that the maximum deflection for that beam is 2.6 millimeter versus 2.86, which is 10% error. And then the formation stress is 27.6, which is 7.5% error with respect to Inventor. Now, if we go to higher number of nodes by increasing the resolution in XYZ, then we see that deflection becomes only with 2% error, and then the principal stress still has quite larger error, 7.3%. Now, we can conclude from our short analysis that, first of all, getting a finite element solution is relatively quick. It took us very few minutes to get it either in Inventor or with Lisa. And this is much faster than any exact solution that we may try. Now, analytical solutions are important to use for simplified model and use them as a reference for the finite element analysis validation. Finite element analysis by any modeling tool must be validated by some second source. It's very easy to get pretty pictures with the finite element analysis which are totally wrong. So we want to make sure that we have a simplified model or another finite element analysis independent which is validating the results. The differences in results between the model, analytical, or different models could be as a result of using different boundary conditions, applying the loads at different locations, using different material properties, using elements with different numbers of degrees of freedom. We'll talk more about that in upcoming lectures, and also using different number of elements. Now, to validate the finite element analysis, we may expect errors around the order of 10%, and that is when the analysis is done correctly. Now, we need to apply safety factor, and that is depending on the failure risk of the design, and it should be in mechanical engineering at least 2. Civil engineers are using on an order of 10. Aeronautical engineers are using it on an order of 20%. And the reason is because otherwise the aircraft may not fly, and at the same time, most of the environmental conditions are known to a high degree of accuracy. Inventor is known to be the most popular CAD system, and it has an integrated finite element for stress analysis. However, to do heat transfer analysis, we need Autodesk Nastran in CAD, and this used in the Inventor CAD models and does the stress and the heat transfer as well. In order to do fluid analysis with Autodesk, we need to have the CFD, which is Computational Fluid Dynamics tools, and that will be a separate software tool. With Lisa, free version, we may use it for strength analysis, buckling, heat transfer, fluid flow, magnetism, acoustic, and electricity powers up to 1,300 nodes for free. And that is, from my experience, a very good tool to back up other analysis tools which you may have in the corporation that you'll be working for. Now, our recommendations based on this simple review is, first of all, to download the free LISA, and this is at www.lisafea.com. And then you could also download the tutorials, which is /tutorials.html, and you'll get a complete set of tutorials that you may scroll down to and get a video description of the process of using LISA. So this is, again, highly recommended. And to finish off the presentation, we like to use, assuming that we have in Inventor as our CAD model, we like to use Inventor for part modeling. We like to run the stress analysis in Inventor. We like to upload the model from Inventor to LISA, or generate a model within LISA to validate the results. We will use Autodesk Nastran in CAD for heat transfer. We will upload the Inventor model to LISA, or generate a new model within LISA and validate the results. And we will use LISA for fluid flow analysis in case Autodesk CFD is not available. So we'll follow this procedure using both Autodesk and LISA modeling in order to solve mechanical engineering problems. This concludes our presentation, and we'll use it in upcoming exercises. Thank you.